Hello again, AP Physics students. In today's lesson, in our unit on math preparation, we are going to start to do some basic calculus. And we're going to do that by examining what it means to take the derivative of a mathematical function, which is going to have a significant use for us when we actually get going through the AP Physics C material. Now, the way the lesson is going to be structured is in the first part, I'm going to go through the theory in terms of like setting up what exactly a derivative is. And then in the second part, we're then going to use a rule called the power rule to take the most simple type of derivatives that we can possibly look at. Okay, so just bear that in mind as we go through this. Kind of like lots of theory to start off with, and then we'll do some more like actual derivatives once we get into the second portion of the unit. Now, the way I'm going to explain this is I'm going to start off by identifying a problem that was actually something we encountered back in Physics 20. So let's say that we have a curve, and what I want to do is I want to consider this curve, which is represented by, which is a function represented by y is equal to f of x, and it's equal to 1/4 x squared. So I actually did plot that that equation using a mathematical program. I think it's called GeoGebra. It's actually a really good program online you can use to like plot graphs. And what I want to do is for that function y equals 1/4 x squared, I want to figure out what is the slope of that function at x is equal to 1. So I'm interested in knowing at x equals 1, what is the slope at this point? Now, back in Physics 20, we did this, okay, because we in the first unit of study on one-dimensional kinematics, we looked at the slope of a position time graph. And back then, the slope of a position time graph represented velocity, or the slope of a velocity time graph represented acceleration. So there were some instances where we had a position time graph which had a direct square variation to it, and we needed to figure out what the velocity was at a given point. Now, the way we did it back in Physics 20 is we constructed something called a tangent line. Now, what a tangent line is it's a line that at that point represents the slope, okay? The slope of that line at that exact point. Now, back in Physics 20, the way I would have explained that you need to draw a tangent line is you draw a line at that point, and then kind of like the spacing between the line and the curve needs to be roughly equal on both sides. So if I just did like a quick sketch of a tangent line here, that looks like a reasonable tangent line, okay? If you look at like the spacing from the line to the curve here, and the spacing from like the line to the curve there, they look like it's roughly equal. Now, the problem is that this is still an approximation. Like, we're kind of like eyeballing where we think those little gaps are about the same size. In fact, if I told like a class of students to like draw a bunch of different tangent lines at that point x equals 1 using this strategy, we would probably all get slightly different tangent lines with slightly different slopes. Now, in the world of calculus, that's unacceptable, okay? Like, we cannot have a ton of error in drawing these tangent lines, and we cannot accept like error in actually calculating the slope. So what calculus is going to do is it's going to give us a way to determine the exact slope at that point, as long as we know what the function of, as long as we know what the equation of that curve is. So this is our problem, the slope problem, and derivatives are going to allow us to overcome this problem and calculate an exact value. Okay, so let's look at the calculus approach. There's going to be quite a bit of a setup to kind of explain how we're going to do this. Okay, so here's my equation, my graph again. Y is equal to 1/4 x squared. And I'm going to label the point a little bit differently. So that point we're going to find the slope at, which is again at x equals 1, I'm now going to call it point P. And I'm going to say point P has coordinates of A is my X coordinate. And then my Y coordinate is going to be the function evaluated at the value of A. So F as a function of A will give you my Y coordinate or value of Y. That's in function notation. So point P, again, we're trying to figure out the slope when X is equal to 1. However, I'm just going to just word it a bit more generically. Instead of us being restricted to X equals 1, I'm just going to say we're at a position where X is equal to A. So that could be a different value. It could be like X equals 2, but in the context of the example we see right here, we're just gonna draw at X is equal to 1. Okay, so that's my X coordinate of point P. It's a value A. The Y coordinate would then be the function evaluated at A. Okay, F of A would give you your Y coordinate. Now, the way we're going to do this is from point P, we're going to draw a second point that is somewhere near, we're going to draw a second point somewhere near point P, and we're going to call it point Q. And this point Q is going to be located a horizontal distance of h units to the right from point P. So I've drawn a little horizontal line to the right showing where we're going to draw point Q at. Okay, so point Q is a little bit over towards the right. If you actually look at the graph here, it would be like one full unit over to the right, but I'm going to draw a second point just somewhere a little bit over to the right by a horizontal distance of h. Now, I also want to identify what the coordinates of point Q would be. Well, if point P has an x coordinate of A, and then I'm adding a horizontal distance of h, then the x coordinate of Q would actually be A plus h, okay? Just the value of A from point P, but we've added that horizontal distance h. And if I want to know what the value of the y coordinate is, I would just evaluate the function at A plus h, that new x coordinate. So that would be f of A plus h. Okay, so now what I have is I have 2 points, point P, point Q, and they're relatively close to each other. I'm then going to draw a line that connects point P to point Q. And this line that connects point P to point Q is going to represent my tangent line. And specifically, it's going to represent the tangent line at point P. Okay, so if I do connect the line between point P and point Q, I would get a tangent line that looks like this. Now, how does that tangent line look? If you look at that tangent line at point P, can you see an equal amount of spacing between the tangent line and the curve? No, not at all. In fact, that's an awful tangent line. If you look at the curve here, so onto the left-hand side, the line is actually below the curve. And then on the right-hand side of point P, the line is actually above the curve. So this is actually a horrible tangent line, okay? If we compare it to like the tangent line we have like by doing the approximation, that one is much better than the one that we can see right here, okay? This is not a good tangent line. We're going to make an adjustment to this to make it so it is a better tangent line in a second. Okay, but let's first of all calculate what the slope of that tangent line would be. Okay, so I just want to figure out what the slope of that line is, and the slope of that line that's connecting point P to point Q. So we know that slope is equal to rise divided by run, where your rise would be the change in your vertical distance from point P to point Q, and your run would be your change in horizontal distance when you go from point P to point Q. Now, I'm going to write this down in terms of the slope formula that we use in mathematics. So in mathematics, my slope formula, the slope equation I can use to calculate slope is m is equal to y2 minus y1 over x2 minus x1. Except in this situation here, we're going to say that point Q is 0.2, and point P is 0.1. Therefore, your slope would be yq minus yp divided by xq minus xp. And what I'm going to do now is I'm going to replace the yq, yp, xq, xp with the variables that you can actually see on the diagram. So this would actually turn the equation into, okay, what's the y coordinate of point Q? Well, it's the function evaluated at a plus h. Subtract, what's the y coordinate of point P? The y coordinate of point P would just be the function evaluated at x is equal to a. Divide by xq. What's the x coordinate of point Q? Well, that's that value a plus the horizontal distance h, and then subtract xp, which would be the x coordinate of point P, which is just as a value of a. Now, we can simplify this equation a little bit here. If we look at the denominator of the equation, I can actually get rid of this a, because we're going a plus h minus a, and that would just leave me with h in the denominator. So your slope, which is your change in vertical distance, divided by your change in horizontal distance, would actually be equal to f of a plus h, subtract f of a divided by h. Okay, that's the slope of the tangent line I see here. But again, the problem is this is actually, the way it's drawn right now, this is a horrible approximation of what the slope is. Okay, because again, like as I mentioned, I clearly can see in the picture that the spacing between the curve and the line is not the same on both sides of point P. So we're going to have to make a bit of adjustment to this, but this is at least the right idea to start off with. Okay, now the way I'm going to make an adjustment is I'm going to move point Q. Okay, so I'm going to move point Q either towards the right or I'm going to move it towards the left. Now, in doing so, if I move point Q towards the right compared to moving it towards the left, it's either going to make the slope approximation better or it's going to make it worse. So let's see what happens if we start off by taking point Q and moving a little bit further towards the right and identifying what happens to my slope approximation. So I said here, a more accurate value for the slope can be obtained by changing the horizontal distance h between P and Q. If you change the horizontal distance h, you change the location of where point Q is going to be located. Okay, so option one is we're going to make h bigger. Okay, h is that horizontal distance from point P to where Q is located. Okay, so initially point Q is located where x is equal to 2. We're going to move it somewhere a bit closer to x is equal to 3. Okay, so now point Q is up there. And let's see what happens. So we draw that point, and then we connect the two dots with a tangent line. And how does that tangent line look? Does it look better or worse than the one in the previous slide? I think it's actually worse. So if you look at this tangent line here, once again, we have the problem where if you look at this side of point P, the curve is above the tangent line, and then over here, the curve is below the tangent line. So this has actually made it even worse. Okay, that tangent line is a worse representation of the slope of point P compared to what it looked like there. Okay, so increasing h is not an option. Okay, to like get a better representation of the slope. Okay, let's try to decrease h. So make h a little bit smaller, which is going to bring Q a bit closer to point P. Okay, so now instead of Q being located at x equals 2, it's going to be located somewhere around like x is equal to like 1.6-ish. Okay, so a bit closer. Now, let's connect the dots with the tangent line. And how does that look? Well, it's getting better, okay? I mean, it's still not good because if you look at the actual tangent line here, I have like some spacing between point P and point, the curve and point and the tangent line here, and I have no spacing on that right-hand side. But if I were at least to compare this to like what I think the tangent line should look like, it's starting to get a little bit better of a representation, but it's still not great. So the question is, what should we do to point Q to make this the best representation of the slope of the tangent line as possible? So what we've seen is that if we bring Q closer to P, it gives you a better approximation. But I wonder how close we could actually get point Q to point P. I think if the closer we could get point Q to point P, I suspect the better representation we're going to have for the tangent line. In fact, the most accurate representation of the slope and the tangent value is when we take h and we start to shrink it. In fact, what we want to do is we want to get that h value so it gets closer and closer and closer to 0. So h is the horizontal distance between P and point Q. So I want to try to make that h value really, 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 really small. Okay, I want it to get close to 0, but not quite 0. If it was 0, then if h was 0, you'd have point Q directly on top of point P, and you wouldn't be able to draw a line. But I want to get it ridiculously close to point P. Okay, so I kind of illustrated this here. So I've said I now have point Q, like very, 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 very close to point P. And what I've said is, what's the value of h? Well, I didn't say what h is equal to. I said h and then an arrow 0. And what that means is that h is approaching a value that's equal to 0, but not quite getting there. Okay. Now, in mathematics, and if you take a calculus course or have taken one of the first things you do in calculus is you spend a great deal of time talking about limits. So what we want h to do is we want h to get close to 0, but not equal to 0. Because again, if h is exactly equal to 0, then point Q would be on top of point P and you could not draw a tangent line. But I want to be ridiculously close to point P. So when we have h approaching, but not quite reaching a value of 0, we refer to that in mathematics as a limit. And we're going to abbreviate a limit abbreviate limit as LIM. Okay, so that's going to be the limit. I'm going to take h and try to get it as close as I possibly can to 0, because that's going to make point Q really, really close to point P, and then see what happens to the tangent line. And if you look at the picture here, if you put point Q like right beside point P, we connect the dots, then this is looking pretty good now. Okay, so now if I look at the spacing between the curve and the line on this side and the curve and the line on that side, it's roughly equal. And this diagram actually still has a little bit of like noticeable spacing between P and Q. If we could get like h to be like 0.0000000000001 or something like that, then my tangent line would be like a pretty darn good representation of what the slope is going to represent. So we want to look at the limit as h is going to approach 0. Okay, so what would the actual slope be? Well, we have to factor this understanding of what a limit is into our equation for slope. Okay, so we identified slope is equal to rise over run, which is your rise is your change in vertical distance divided by your change in your horizontal distance. Now, if you look at here, we already derived this part of the equation from before. Okay, so we plugged in the values of yq minus yp divided by xq minus xp, and we ended up getting f of a plus h minus f of a divided by h. Now, the one new thing that we have here is we've added this little symbol on the left-hand side where it says lim, and then below that, it's telling me what I'm doing to h. So what this is saying is my slope is the limit of this equation as you take h and get it closer and closer and closer to 0. Because the closer and closer you get h to 0, the closer point Q gets to point P. The closer point Q is to point P, the better representation of I will have of my actual slope. Okay. And this is going to be the way in which we define slope in calculus. So the slope here is going to be the limit as h approaches but doesn't quite get to 0 of f of a plus h minus f of a divided by h. Okay, so now we're going to talk about, like, okay, what does this have to do with this term I've used before, a derivative? Okay, as a general definition, a derivative, when we talk about like math or just some kind of like physical application, a derivative is a rate of change. So in the problem we looked at, a derivative would be the rate at which one variable changes with respect to another one. So it's the rate at which the rise of my slope triangle is changing with respect to the run of the slope triangle. In calculus, instead of using the triangle symbol to show that a quantity is changing, we use the symbol d instead of the Greek letter delta. That's just the common like notation for showing that we're dealing with a derivative. So a derivative, the abbreviation would be a d. Therefore, instead of writing down delta y over delta x, we would write down dy over dx. So what dy over dx means, it's the rate at which the height of your slope triangle, the slope would be changing with respect to the horizontal distance of the actual slope triangle if you're envisioning a slope triangle. So delta y over delta x is equal to dy over dx. Now, there are a couple of other ways of writing this that indicate that we want to look at the derivative of a function, which is my rate of change. So dy dx, we never use the delta notation, okay? The delta notation is not used in calculus at all. Other things we can do that indicate we're looking at an actual derivative of a function is if we have a function y, we write down a little prime symbol beside it. So y prime would mean the derivative of y with respect to x, which is the rate at which y is changing with respect to x. Or in function notation, we could write down f prime of x, which means it's the derivative of the f as a function of x, which is equal to y with respect to the variable x. Okay, so just a couple different ways that we do write it. Depending on the problems we're dealing with, sometimes it's more convenient to use the y notation, sometimes more convenient to use the function notation. Depends on like how the equation is being presented. Now, in terms of the problem we looked at, so I said a derivative is a rate of change between, in terms of how one variable changes with respect to another one. Well, in the context of like our slope problem we are looking at, so we're looking at how the rise changes with respect to the run. Well, that is a representation of the slope. So in mathematics, when we're looking at like an actual function, what does the derivative of a function represent? Well, the derivative of a function represents the rate at which the rise is changing with respect to the run, and that is slope. So therefore, if you have a function, y is equal to f of x, the derivative of that function is going to give us information about the slope of a tangent line at a point that we are interested in. Therefore, we can say my slope, which we know is equal to delta y over delta x, rise over run. In derivative notation, that would be dy over dx. In the prime notation, that would be equal to y prime or f prime of x. And we know that dy dx, okay, we showed this on the previous slide. Okay, let's go back to the previous slide for a second. We identified that delta y over delta x is equal to the limit as h approaches 0 of f of a plus h minus f of a divided by h. Okay, so instead of writing down delta y over delta x, you write down dy over dx. Now, I did change one other thing here. So I said the derivative of the y with respect to this is how we word it, by the way. We say the derivative of y with respect to the variable x is equal to y prime, or f prime of x, and that's equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. Now you'll notice here that I replaced a with x. That's just because we want to make this more general. If I say a, that's supposed to have like a fixed value along the x-axis. If I say x, then it does not have a fixed value. Okay, it could be like any value of x along the x-axis. Now, this equation here is what we refer to as being the definition. So I'll write this down. This is what we call the definition of a derivative as a limit. So like I mentioned, one of the first things you typically do in a calculus course is you get introduced into determining the limits of functions, and then you kind of take it a step further and you talk about how a limit applies to figuring out the slope of like a tangent line. And that's what a derivative is. A derivative is just the slope of a tangent line at a given point, okay? Given point x comma y. Now you'll actually calculate derivatives like in your calculus courses using this definition of a derivative as a limit, but it can be a little bit annoying and a little bit tedious. So what we're going to do is, instead of using the definition of a derivative as a limit, we're actually going to use established rules that are going to allow us to do this much more quickly, okay? Because like we're interested in doing derivative calculations as fast as possible, and derivative calculations as fast as possible do not involve using equation number 1. Okay, so I'm going to start to introduce you to a bunch of these different rules now. So the rules I introduced you, they actually can be derived from that equation, the definition of a derivative as a limit. But I'm not going to show you how we get them. I'm simply just going to present the rule, and then we're going to start to use them right away, because that's what we need to do. Okay, so we have a bunch of rules that allow us to differentiate. And when you see that word differentiate, it means we're going to find the derivative of a function, and the derivative of a function is going to give us information about the slope of a tangent line. Okay, so we'll start off with the most basic rule. Actually, there's one other rule that's a little more simple than this one. We'll start off with like essentially the most simple rule, and that is what we call the power rule. So let's say that we have an equation, y is equal to f of x, and that is equal to x to the power of n. So as an example of this could be like an equation where you have, I could say like y is equal to x to the power of 20. Okay, so I have a variable, single variable, with a power attached to it. Now, if I want to calculate the derivative of this function, so dy dx, which means let's figure out the derivative of the function y with respect to x, which is going to tell me what the slope is of a tangent line. Then the derivative of x to the power of n with respect to the variable x can be calculated as follows. This would be n, and then x to the power of n minus 1. Okay, here's essentially what happens when you're doing like a derivative of a power. If you have x to the power of n, what you do is you take the power and you move it in front of the variable, so it now takes the place of the coefficient. So when you do that, you would then have n x, okay? So the n is now in front. And then what you need to do is you subtract the exponent by 1. So you would put the power in front of the variable, and then the new value of the exponent would just be subtract 1. So in this example I showed up here, where I have y is x to the power of 20, if I said let's calculate the derivative of y with respect to the variable x, this would be equal to, okay, we move the 20 down in front, So that would be 20. And then it'd be x to the power of 20 minus 1. Therefore, the derivative of y with respect to x would be 20, and then it would be x to the power of 19. Okay, that rule that I've boxed and numbered as number 2, that is what we refer to as the power rule. Okay, so again, the power rule, because we're looking at like the power attached to like a specific variable. Okay, let's look at some examples here. So it says differentiate the following functions. Okay, so let's look at A. Now again, there's different ways you can identify that you want to figure out the derivative of a function. So one thing you could do is you could write down dy dx if you wanted to. So that's perfectly fine. So I could write down, so I have y equals x to the 5, therefore dy dx would be equal to, okay, so what do we do here? Use the power rule. Take the power, move it in front of the variable. So we'd have 5x. And then what do you do to the exponent? You take the exponent and you subtract 1. Therefore, the derivative of y with respect to x would be 5x to the power of 4. Okay, that's the derivative of the function x to the power of 5 with respect to x. Okay, so we'll box that. Okay, B, it says f of x is equal to 1 over x squared. Now, the issue here is that I have my variable in the denominator of this equation. If I want to truly use the power rule, I want to rewrite it so I have the variable in the numerator. So I can do that pretty easily. I can just rewrite this as f of x will be equal to, just invert this thing here, it would then just be x to the negative 2. Okay? So 1 over x squared is equivalent to x to the power of negative 2. Now, let's say we want to figure out what the derivative of this function is. Okay, so another way to indicate we're finding a derivative is you can use the prime notation. So what I can do here is I can write down f prime of x. So what that means is we're going to figure out the derivative of the function with respect to the variable x. And then we use the power rule. Okay, so the power rule involves take the exponent, move it in front of the variable, and then you need to adjust the power, and we adjust the power by subtracting 1. Okay, so this would then be negative 2 x to the power of negative 3, or if you wanted to then rewrite it out with the positive exponent, you could write down f of x, x prime of x, would be equal to, and this would be fine if you wrote it like that, but you could write down negative 2 divided by x cubed. Okay, and we can box that. Okay, C says y is equal to x. Okay, so we could, again, you can use different types of notation. I can use the prime notation for y as well. I can write down y prime. So y prime just means take the derivative of the function y with respect to x. Now, for this one, so y prime, okay, what's the power attached to the x? It's a 1. So what are we doing here? We're just moving a 1. We're not really doing anything to the actual coefficient because the coefficient's already a 1. So by moving that 1 down there, it would just turn it into 1. And then you'd have x to the power of 1. But then again, you have to subtract that 1 here. Okay? So y prime would then be 1x to the 1 minus 1. And then this would be y prime is equal to 1 x to the power of 0. And then y prime would be equal to x to the power of 0 is 1. It would just be 1. Now, I just wanted to point something out here. Like let's say we sketch that graph, like y equals x. So if I like just quickly did a sketch here, y equals x. Y equals x is just a line that passes through the origin and has a slope of 1. So if I were to plot this, it might look something, oh, let's try to actually get it so it goes through the origin here. Okay, so this would be a line that just goes through the origin and it has a slope that m would be equal to 1. We know that from like just writing it in the form y equals mx plus b. Okay, so but look, the derivative actually tells me what the slope is. Remember, the derivative of a function tells you what the slope of a tangent line would be at any point. Now, because this function here is already a straight line, it must have a constant slope. It doesn't matter if you draw a tangent line up at the top here or up at the bottom. It's going to be the same tangent line because the slope is not changing at all. So what we did here is we actually proved this using calculus. We said, okay, we have the function y equals x. Let's figure out the derivative of that function, which should give me the slope. And it turns out the derivative of that function does give me a slope of 1. So that does match up correctly. Well, how about d? Okay, so d is you have f of x is equal to 4. Okay, now we should be able to predict what the derivative is if we're even taking it. So if I just quickly sketch like a Cartesian plane again, so you have y, and then you have x. F of x equals 4 would just be a horizontal line that passes through the y-axis at 4. Okay, so what's the slope of that line? Well, horizontal lines have a slope of m is equal to 0. So we should be able to take the derivative of this function and then identify that the slope is equal to 0. Okay, so let's see if we can actually go ahead and do that. Okay. Actually, it turns out here that if we use the power rule in this situation, it doesn't quite work out correctly. But because there's another rule I'll give you in a second, the constant rule. Maybe we can come back to this. Actually, maybe I should introduce the constant rule right now. Then we'll come back. Okay. Okay. Constant rule tells you if y is equal to f of x is equal to a constant c. So that could be like right here, y is equal to f of x equals 4. And it turns out the derivative of any constant is equal to 0. Again, that should make sense because if f of x is just a constant value, that means it's a horizontal line. Horizontal line has a slope, therefore the derivative of this function should be equal to 0. So therefore, what I could say here is we could write this in prime notation. We could say the derivative of the function f with respect to x would just be equal to 0 because the slope of this graph is 0. Okay, so anytime you just have a constant on its own, the derivative of a constant must be equal to 0 because any constant function would be a horizontal line and horizontal lines don't have any slope. So that would be equal to 0 there. Okay, so that's my constant rule. The derivative of a constant with respect to x is just equal to 0 because it's telling you figure out the slope of a horizontal tangent line, or sorry, a horizontal line, and that would just be equal to 0. Okay, we have another rule that's called the constant multiple rule. So the one thing you'll notice right here is that all of these functions do not have a numerical coefficient in front of them except for a value of 1. So what if you have a numerical coefficient? It says if y is equal to c times f of x, where c is a constant and f of x is a function that you can take the derivative of, then the derivative of c, the constant, times f of x with respect to x would just be equal to, it's like you can factor the constant out. You can pull the constant out of the derivative part of the equation, and you can just figure out what the derivative of the function is. So here, let me give you an example of this. Like, let's say that we had f of x is equal to, I'll say like 5x to the power of 7, okay? So now I have a numerical coefficient in front of here. Okay, so if I want to figure out the derivative of this function, so I could say f prime of x. What you do is you don't even worry about the constant. So what you can do is you can just simply ignore the constant, because what you can do is you can pull the constant out of the derivative here, okay? So you can pull it out, and then you can simply just figure out the derivative of the function that has the x value that's attached to it, okay? So then this would just turn into, don't worry about the 5, the constant, and then we just use the power rule to take the derivative of this function. So the derivative of x to the power of 7 would be 7 x to the 7 minus 1, or f prime of x would be equal to 5 times 7 is 35, and then it would be x to the power of 6. So that's all it's telling you right here. If you take the derivative of a function that has a constant in front of it, we can actually just pull the constant out, don't take the derivative of it. And when I say a constant, I mean like a numerical coefficient, like a constant multiple, and then you can just take the derivative of the remaining function. Okay, and that's my fourth little, my fourth equation. Now let's go back to that first function. So we started the lesson off by me introducing the curve y is equal to 1/4 x squared. And the whole issue is trying to figure out what is the exact slope of a tangent line at x is equal to 1. Now, we're going to do this with calculus now, okay? We're going to use the power rule to do it. Okay, so I have y equals 1/4 x squared. So I'll write down my work here. I'll write it just down in y notation instead of function notation. So you know what? Function notation is fine. Let's go f of x is equal to 1/4 x squared. And we want to figure out, okay, what's the slope of a tangent line at that point? Okay, so to figure out the slope of the tangent line, take the derivative of this function. So that would be f prime of x would be equal to, now, this is the constant multiple rule. We don't have to worry about this numerical coefficient in front. Okay, we just leave it as it is. And then we just take the derivative of the actual function here, okay, x squared. So the derivative of x squared would be move the power down. So you have 2 x to the 2 minus 1. And then this would give me 1/4. And then you'd have 2 x to the power of 1, in which case we just write down x. And then this fraction can be reduced. So what you could do here is you could 2/4 reduces to 1/2. Therefore, I would have f prime of x would be equal to x divided by 2. Now, if you're wondering what this equation does, this equation can actually tell you the slope of a tangent line at any point along the graph. Like if I want to know what the slope of the tangent line is at x equals 1, all I have to do is plug in x equals 1 into the equation. If I want to know the slope of the tangent line at x equals 2, I just plug in x equals 2 into the equation, okay? Because again, this right here, the derivative tells me what the slope is. This is very powerful, okay? Because what I have now is I have an equation that I can be used to identify what is the slope at any point along this entire curve. Now, we were just interested to start the lesson off and figuring out, okay, well, what's the slope of a tangent line when x equals 1? Okay, so we want the slope when x is equal to 1. So all I'm going to do is I'm going to evaluate this, this derivative when x equals 1. So I would say the derivative of the function when evaluated at x equals 1 would just be 1 over 2. Or if we wanted to, we could write it down as a decimal number. We could say the derivative of the function evaluated at x equals 1 equals 0.5. Okay? And the derivative of a function represents your slope. So that's the slope of the tangent line, the exact slope of a tangent line at that point. Okay? So again, this is like the power of a derivative. If you know what the equation is, and you know like some simple derivative rules, you can take the derivative and then you have an equation where you can use to figure out the slope of a tangent line at any point. Now, if you went over to x equals 2, we would just plug in 2 into the equation. So that would turn it into 2 over 2, which is 1. So therefore, the slope is bigger, which is not surprising because I can see that the curve is actually getting steeper as you go towards the right. Now, C says, okay, let's get an equation for the actual tangent line. Now, so the tangent line, which I don't think I can sketch here because I don't have access to a line. So what is it? I mean, if I try to draw a tangent line, it would be, I mean, I'll do my best to sketch this. This is going to look awful though. Okay, so let's try to do my best at this. So oh my goodness, that's so bad. Okay, how about I cheat? I'll use an actual line from Microsoft Word. Okay, so let's keep this. Let's insert a line. Let's go to a shape here. Okay, and oh, here's my line. Okay, let's see if I can change the color. Actually, it's okay. We don't need to change the color. All right. Roughly speaking, that's my tangent line. Let me move it down a little bit. Okay, good enough for now. Okay. I mean, that's not the perfect tangent line. We need to know the exact slope to get this thing here. Let's move it just a little bit over. So now let's go back. Okay, now I've got my tangent line on here. Okay, now I want the equation of the tangent line. And when I say the equation of the tangent line, let's give it in the form y is equal to mx plus b. Now, the problem I have right now is I do know what the slope is, okay? So the slope is 0.5. Yeah, write the equation of the tangent line. I'll say at x equals 1, because depending on which value of x you're at, the tangent line is going to look different. Okay, so we've got to figure out what the value of b is. Now, to figure out the value of b, we need to know a point that is actually on the tangent line, okay? Now, there's one point that is shared between the curve here, and that's shared between the tangent line, and that's this point at x equals 1. So what I can do is I can just take the equation, 1/4 x squared, and then figure out what is, by plugging in x equals 1, figure out what the value of y is, and then I can figure out what the tangent line is. Okay, so the way I would do this is, okay, so we know y is equal to 1/4 x squared. Now, both the tangent line and the curve actually touch each other at x equals 1. Okay, so that's like a common point they share. So then the value of y would be 1/4 times 1 squared. And this would then be equal to 1/4. Or if you want to, you could write it as like a decimal. You could write it as y is equal to 0.25. Therefore, this point here would actually have coordinates of 1 and then 0.25. Okay, and then to figure out what's the equation of the actual tangent line, well, we're trying to figure out what the equation of this line is. We know this line has a point x1 comma y1, and we know what the slope is. It's 0.5 because we determined that from the derivative. So if you want to, you could use the slope point formula for math to figure out what the equation is. So we'd have like y minus y1 is equal to m, and then x minus x1. Okay, so I go y minus, well, y1 is 0.25 is equal to m, which is 0.5. And then this would be x minus x1, which is 1. Okay, let's do distributive property here. So this would then turn it into y minus 0.25 is equal to 0.5x minus 0.5. And then if you just add 0.25 to both sides of the equation, you'd then get y is 0.5x, and negative 0.5 plus 0.25 would be negative 0.25. Okay, so that's my equation of the tangent line. Okay, I got the slope from figuring out the derivative, and then to get the y-intercept, I just had to identify a point that was actually on the tangent line. Now we can actually fix the line so it looks a little bit better here, because if I look at my graph, actually that's not bad, okay? Because I think like each increment on the graph it goes up by 0.2s, 0.4, 0.6, 0.8. So that'd be 0.2, and that's just a little below it. So that actually, believe it or not, I actually did a pretty good job just by drawing that tangent line there. Okay, so this is a huge use of like calculus where we can use it to figure out the exact slope at a point on like some kind of mathematical function. Okay, let's look at one other rule, and then we'll stop the lesson and we'll look at a more complicated rule in the following one. Okay, let's say we have two functions. We have f of x and we have g of x. They're both differentiable, which means we can take the derivative of both of them. Now, let's say we want to figure out the derivative of some functions that are being added together. So you have the derivative of f of x plus g of x with respect to the variable x. It turns out you can just figure out the derivative of each function separately. So you figure out the derivative of f of x with respect to with respect to x, plus a derivative of g of x with respect to x. Find those two derivatives separately, and then just add them together. And that also works for subtraction as well. So if this was plus or minus, like this could also be plus or minus here. And that's equation 5. Now, you cannot do the same thing for division though, or multiplication. Like if you had like f of x times g of x, it would not just be the derivative of f of x times the derivative of g of x, nor would the derivative of f of x divided by g of x be derivative of f of x divided by derivative of g of x. Now, I'm not going to teach you these rules in AP Physics because like I've never seen an AP exam question which required us to utilize the product or the quotient rule. So we don't really need to use them. However, like you for sure in your calculus course are going to learn what you do if you have two functions multiplied together or divided, and how do you figure out the derivative of them. But it's not as simple as just adding or subtracting. There's a more complicated rule involved with this. Okay, let's finish this off just by applying this rule now. So I have a function y is equal to 2x cubed minus 3x squared minus 12x plus 1. And the first thing I want to do is I want to differentiate this function. Now, the thing to notice up here in terms of how this is different from our previous functions is that there's a bunch of terms, okay? A bunch of separate terms here. Now, you could treat these as like a bunch of different functions. You could call this one 2x cubed f of x, g of x, h of x, I of x if you wanted to. But what the sum rule tells us is that we can just figure out the derivative of each term individually and just add them all together, okay? So it's actually really not that hard to do. Okay, so let's use the notation. We'll do dy dx. So I want to figure out the derivative of the function y with respect to x. Okay, so we just do it in parts. So first of all, let's figure out the derivative of 2x cubed. Well, the 2, we don't need to worry about it. Okay, it's a constant multiple. And then we just take the derivative of x cubed, which would be 3. Move the power down, x, and then 3 minus 1. Okay, so that's a derivative of the first term. And then we would subtract 3. And again, subtracting 3 here, the minus 3 part is a constant multiple, so we don't have to worry about that. So we can just take the derivative of x squared, which would be, move the power down, and this would then be 2, x to the 2 minus 1. And then we have minus 12x, so we go minus 12. And then, again, this would be like x to the power of 1, so it would be the same thing as going like 1, x to the 1 minus 0. And then the final one is, okay, what's the derivative of a constant? Remember, a constant, if you looked at it as just a separate function, a function f of x equals 1 would be a horizontal line. So that if the derivative is the slope, what would that derivative be equal to? Well, it would just be add 0. Okay, the derivative of a constant is 0. Okay, let's clean this up a little bit. So this would then turn into dy dx would be equal to 2 times 3 is 6. X to the 3 minus 1 would be x squared. Subtract 3 times 2 is also 6. And then 2 minus 1. So that would just be 6x. And then here, this would turn into, this is x 1 minus 1, not 1 minus 0 there. My bad. Let's fix that. Yeah, we're subtracting 1. An interesting thing to note, by the way, anytime you take the derivative of a function, it actually reduces the power by 1. Well, for these functions anyways. Other more complicated functions, there are some other funkier rules with them. I just want to point out, this would actually give you x to the power of 0. And x to the power of 0 is 1. Therefore, we would just be subtracting 12 here. Okay, so that's the derivative of that function. 6x squared minus 6x minus 12. And again, what does a derivative tell me? It's an equation I can use to calculate the slope of tangent lines at any point on the graph. Okay, now let's try to utilize this. So B says calculate the values of x where the graph will have horizontal tangents. Now, we should be able to see this. So when it says horizontal tangents mean that you don't have, your slope is 0, okay? So if you drew a tangent line, it would just be a horizontal line. Now, that would actually be at the top of this hill here, okay? So the top of the hill, you would have a horizontal tangent. And then also at the bottom of the hill here, you would have a horizontal tangent, okay? So we're going to try to use this equation to figure out, okay, well, what's the value of x at this horizontal tangent? What's the value of x at this horizontal tangent? Okay, so let me clarify this. I'm going to say the graph has horizontal tangents. When your slope is 0. Okay, if your slope is 0, then that means that dy dx, the derivative of y with respect to x, would be 0. So what I'm going to do is I'll take this equation, replace dy dx with 0, because what I'm doing is I'm saying, okay, let's figure out the values of x when your slope is 0. Dy dx is 0, your slope is 0. And then we have to solve for x. So this would be equal to 6x squared minus 6x minus 12. Here's another important use for derivatives. You can use derivatives to figure out where the minimum and the maximum of a function are, because a minimum or a maximum of a function is a spot where you have a slope change. And a spot where you have a slope change is where you have a slope of 0. So if you just identify that, okay, your slope is 0 when you have like a horizontal tangent, you can then figure out, okay, what's the location of these minimum and maximum values. Okay, let's solve for x here. Now we need to factor to do this. So this would be 0 is equal to, let's first of all pull out a 6. So we pull out a 6, and then we'd have x squared minus x minus 2. And then this would be, now we can factor this trinomial just through like trial and error. So this guy would factor to x minus 2. X plus 1. And then the values of x here are going to be when dy dx, the slope is 0. So what values of x would make this equation 0? Well, if you plugged in x equals 2 here, it'd be 2 minus 2, which is 0. So that would be one solution. And then the other one would be, okay, if you plugged in negative 1 here, negative 1 plus 1 would be 0. That would be the other spot where you would have a slope of 0, or horizontal tangent. Does that look about right? Yeah. X equals 2 here. And then here, if that's negative 2 and that's 0, that looks like it's about negative 1. So again, there's a lot of like really important uses for derivatives. Again, it allows us to like, again, figure out the slope of like a function, but you can do like some other things too. Like you can figure out like what the slope of a tangent line is. You can figure out what the equation of a tangent line is if you take it a step further. You can figure out where you have minimum and maximum points, all sorts of different things. Okay, so that's it for this lesson. So again, this was like a basic introduction of calculus. So I tried to introduce it by talking about the slope problem, and then I transitioned to talking about how a derivative of a function tells you the slope of that function at a given point. And then we introduced the power rule, which is a very quick and efficient way to determine what the derivative of a function is. And then in the next lesson, we're going to look at some more complicated functions that go beyond the simple power rule. And I'll talk to you then.